That is the constraint. Got it. That's our relationship, you might say, between these two variables. Again, we're going to try to render the volume of the cylinder univariable. So we need to get rid of one of these two. If I need to get rid of one of these two, what I need to do is find a relationship between these two. And that's exactly what this does. We now have a relationship between the height of the cylinder and the radius of the cylinder. And it's going to have in it, it turns out, the height of the cone and the radius of the cone. Now, these two are variable, right? We said the height of the cone changes, the height of the cylinder changes and the radius of the cylinder changes. But these, the height of the cone and the radius of the cone, do not change. So this is really just two variables here, and the rest is all constants, right? So there's our two variables. And looking back at the volume function that I'm going to have to differentiate, what I should do is, in this case, solve for hc, because I would prefer not to have to square any type of expression I would have to. If I can just solve for hc, it's probably a cleaner substitution than solving this constraint for r. So I'm going to solve for hc instead of rc, just because of the way the volume structure looks. Okay? It doesn't always work out that way, but it makes sense in this context to do that. So I need to solve the constraint for hc, so as to substitute into the volume function, right, which is our objective function. So hc in here, it looks like if I just multiply by rc, all right, that'll be a good start. So I would have h minus hc equals h on r times rc. If I want hc by itself, I just switch basically hc with this expression here on the right, switch the two. Okay, so if we do that, I'm thinking it looks something like this: hc equals h minus h on r rc. All right. Now, h is a constant, so I could factor that off. Right, this would be the same as h times 1 minus rc on r. 1 minus the ratio of the two radii. Okay, so there's hc. Let's go ahead and put that into the objective function now. Right? Here's our objective. Let's go ahead and substitute it in now and see what we get. So we should have volume is pi r squared h. So volume function now will just be in terms of rc. We'll have no hc in it because we're going to replace it. We have pi rc squared, and instead of h, I'm going to put, instead of hc, I'm going to put h. Maybe use a bracket. Use h times 1 minus the ratio of the radii, where again rc is the variable and cap r is a constant. All right, so we now have a univariable volume function which we can differentiate and set equal to 0 and use the first derivative test on. So as before, if we think about it, remember rc is the variable. That's what I was trying to say at the very beginning of this problem. Try to keep your eye on what is variable and what is constant. rc is the variable, so therefore really this is like a cubic function, right? If you multiply rc squared into here, which I'm going to do right now, I'm going to take the h out, it's a constant, all right? Pi h together on the outside, they're just being multiplied together, and on the inside I would have rc squared times 1, so rc squared, and then I would have minus 1 on r, 1 on cap r, rc cubed. All right? So there is our volume function written as a third degree polynomial in RC. I need to take its derivative. So v prime of RC, the derivative will bypass these two constants, they just stay there. I take the derivative of this with respect to RC, because it's the variable. 2 comes down, so 2RC minus 3 on R, that cap R is a constant, RC squared. set equal to 0. All right, we should be able to factor off RC now from this expression. Again, the reason I multiplied it through in the first place was because it makes it easier to take the derivative. But once I got the derivative taken, I'm setting equal to 0 and solving, so I want to take out any common factors. It looks a little redundant at first, but it's really not. So pi h RC, the variable RC, 2 minus 3 on cap R RC to the first power equals 0. Now we have two options. Clearly RC could be 0, and that would make this true. The other option is 2 minus 3 on RRC would be 0. I'll just write that here. 2 minus, we'll solve it in 1 second. It's not too complicated, really. So I need to solve for RC. Right? This would imply, if I just subtract 2 over and then multiply by the reciprocal, what do I get? Something like the radius of the cylinder would be 2/3 the radius of the cone. Okay. All right. So those are our two critical values. Two critical values we have there. RC is 0 and RC is 2/3 R.